Well, welcome. As I said last time, this is aimed at new starters, but all are welcome, and particularly those folk who are more experienced. It's really helpful to get your comments in, like, we discussed this 6 months ago and I found it very interesting. Could we talk about that? You know, those kind of things is very, very helpful. So please contribute as we go. What I'm going to talk about today is how ground loop design works and the factors that influence it, what resources we've got, what borehole design actually looks like. I'm going to do a quick software demo for those of you who haven't seen it before. I'm going to talk about questions we can ask the client to not only make design process easier, but also to help you as a sales tool as well, because there's quite a number of little tricks that I certainly used over the years. I know you'll be very familiar with it, David, of the questions you can ask the client to get them to buy into the technology. I'm going to talk about heating and cooling loads as well, and then finally then about hourly, half hourly, monthly data and so on. So that's today. Next time, in 2 weeks' time, I think it is, Duncan, is that right? I'm going to then build on what we talked about, a little bit more detail on thermal response testing. I'm going to then talk about the hydraulics of systems, and we'll probably spend more time on hydraulics than anything else when we're doing a design. So it's just worthwhile doing a bit of that. Again, it's familiarising you with what we do. And then I'm just going to talk about the reports, particularly for the new starters, about the value of our initial geology reports, particularly to help go forward with that. And then we've got session 4 towards the end of February, which we'll be talking. I'm kind of seeing that one as half presentation on risks and then half Q&A. So if you've got any questions that you think might be deeper or anything like that, then we'll put them into that session. And then finally, we're going to have the value add, 5 for the price of 4. We're going to have a session on mines, which we actually did at a conference, Kensa conference last year, and we're just going to rerun that with a way of getting, getting everybody to see that, but also so we've got a recorded version of it so that people as they start can flick through it. We found that quite useful internally. All right, so without any further ado, unless anybody's got any questions or comments, I'll start on how ground loop design actually works. Is that okay? No comments in the chat yet, Duncan?
No, you're clear to go, Chris.
Clear to go, right? Okay. So what I've got here is a very simple schematic of a heat pump in heating mode here, this side, and this is in cooling mode on that side. And what we are doing in the heating mode is we're putting cold water into the ground, and that then naturally sucks heat in from the ground around it. And in cooling mode, we're then doing the opposite, so we're putting warm water into the ground, and that's pushing heat away from the pipe. Okay, heat of extraction here, and that's the heat being extracted from the ground, and this is the heat of rejection, the heat being rejected into the ground here. Okay, so heat of extraction, heat of rejection. We actually use the same terms on the load side of the system. So this is the heat being rejected by the heat pump, heat of rejection, and this is now the heat of extraction from the heat pump. Okay, there is an additional amount of energy involved in this, and it's the electrical energy here. Okay, so both of these processes, heating and cooling, use electrical energy to drive the heat pumps. And if your heat pump's well designed, as all Kensa heat pumps are, then almost all of that electrical energy in heating effectively adds to the heat coming from the ground and becomes the heat of rejection. So your heat of rejection is your heat of extraction plus your electrical energy. Okay, sorry, my drawing's not very good because I can't put my hand on the screen. Now, the important point there is that the heat of rejection, so the heat going into the building, is not equal to your heat of extraction. Okay, so when we're doing a ground loop design, we are telling the design software what our heat of rejection needs to be in the building, both in terms of peak loads and in terms of the annual demands. We're telling it what the heat of extraction is if we've got cooling loads going on, but that is not equal to what's going on in the ground. Okay, so that's a really important point, and you'll often see consultant engineers who don't maybe understand it, they'll be assuming that these two terms are equal. And it's you know, schoolboy error is the old phrase goes to do that. Slight difference when we're getting into cooling, because that electrical energy now ends up in the ground rather than in the building. So our electrical energy in heating mode helps us. It adds to the heat being rejected into the building, but actually hinders us in cooling mode. So that heat is also being put into the ground. So a balanced system, as far as the building's concerned, is probably not going to be balanced in terms of the ground, or it certainly isn't going to be balanced in terms of the ground. One final refinement, you can't often use a ground loop to cool directly, so we don't actually need a heat pump in here, in which case obviously your heat of extraction and heat of rejection will be very close to each other. So there are refinements there if we've got a passive cooling circuit, as we have got, for example, on the shoe boxes. We're quite regularly doing that now, well, reasonably regularly doing that now.
Chris, Steve has asked, how does simultaneous heating and cooling work at the same time? Is it separate boreholes?
No, you absolutely use the same. You use the same boreholes. So let me just drop into my whiteboard very quickly and show you what that looks like. So this would be a classic heating and cooling ground source system. So what we've got here is we're all sharing the bore field there. And the point of that is, if we've got heat being taken out of the building by this cooling heat pump, it goes into the ground loop and comes back out pretty quickly and becomes heat. It becomes heat in the building. So you've got simultaneous heat recovery. But the best way of thinking about this, this way we're connecting here, is that imagine your ground loop, it's like a spring and a damper on a car. If you've got an imbalance, as we have here, we've got heat pump 1 and heat pump 2 heating, and heat pump 3 is cooling. We've got an imbalance of what's going into the ground and what's coming out of the ground. So this takes up the slack for you. So in a heating and cooling system, you absolutely do want to be sharing the ground loop. There's very, very few exceptions to why you would want to do it differently. Using the ground loop as that heat recovery mechanism is probably the biggest strength of what we do when we're talking about heating and cooling projects, and other forms of heat recovery as well. Great question. Who's that from? Steve?
Yeah, Steve Young.
Brilliant. Great question. So one final thing that we want to mention on this is how do we define our coefficient of performance, how efficient this process is. So what I tend to think about is what's the customer interested in? Well, the customer's interested in what's going into the building and the electrical energy. So it's the heat of rejection divided by the electrical energy is your COP, okay? In that instance. Different here, of course, because the customer's now interested in the heat being extracted from the building and the electrical energy. So it's the heat of extraction divided by the electrical energy. So slightly different definition, but at the same time, that's the COP, coefficient of performance, okay? All right, any questions on that before we go into the next bit?
No, we're good for the next slide.
Excellent, okay, cool. So that's how design works. This is the building. There's the characteristics of the heat pump. How much pipe do I need to put in the ground is the basic question. I'll come back to that in a second. But the factors influencing it are geology. And the three key terms in geology that we're interested in is the conductivity, the diffusivity, and the temperature of the ground. The conductivity is how quickly the ground will give you heat. Diffusivity is how quickly a temperature wave will propagate through the ground. And the understood ground temperature is obvious. It's the temperature of the ground before we start messing around with it. And what we do is we determine that by using geological maps. This is a layer in Google Earth of the UK and Republic of Ireland geology. And if you zoom in on that, you can get some detail on where it is. It's a pretty high level tool. We actually use more sophisticated tools available from the British Geological Survey to assess what's going on in the ground. Now, you might think from this that, you know, out here in Norwich, it's just the green stuff, which is chalk, all the way down. Well, actually, you'll get through the chalk at some point and you'll be into either the greensand or Norwich crag, one or the other. So it's in layers. So just don't be fooled by a simple map like that. The strata is in layers and it can be very, very complex. Every type of geological condition that exists everywhere in the world, except two, exists in the British Isles. and so it's probably the most complex geology anywhere in the world. So it really is important. We've got 3 geologists in our team, and we are regularly bouncing stuff off each other. What do you think of that? Duncan, your favourite geology is Bristol, isn't it? Which is pretty horrible as far as trying to work out what's going on there is concerned, because it's been folded and fissured and cracked and so on over millennia. So a very, very complex geological condition. And the records that we've got available to us vary. So if you can go up to the north of Scotland, particularly in the islands, and there might not be any borehole records from existing boreholes for 20 miles or even more. So you really are working on trying to triangulate what's going on around those points. So the thing about geology is it's not a precise science, it's not physics, it's not maths. It takes a bit of interpretation, and really the key thing is it takes experience as well. So we've probably must have probably 80 years of geological experience in our team, and we rely on it all. So that's the geology.
Probably with geology there, Chris, it's probably worth adding the most commonly made mistake that I see when people trying to use lookup tables and the BGS and geology website to do their own rule of thumb designs for sizing ground loops. They see the bedrock geology and assume it's that going all the way down, whereas it can be only a metre thick.
Yep.
Until you get to the next layer.
Absolutely. I'm going to talk, in fact, it's a very good point you make, because I'm going to talk about hydrogeology now. So this is not just the native properties of the rock, but also the water that's in the ground. And this is a map, very high level map of the major aquifers in the bedrock in the UK. And you might think that this purple stuff's the chalk, and it's a major aquifer, really significant aquifer. And you might think that, whoa, there's no chalk under London. Well, actually, this purple stuff extends underneath. But the map that the BGS publishes just shows the first level of rock. And the first level of rock in London is London clay, which is impermeable. The chalk does exist underneath it. So I've done many, many dozens of open loop from water well projects. And if you're unfamiliar with those terms, we talk about the different types of systems last week. Done many of these projects in central London, including Buckingham Palace, for example. It's got an open loop system in it. So the hydrogeology is very important, and understanding how these maps work takes a bit of time. The hydrogeology is important to us from the point of view of, can we do open loop? Can we take water from the ground, warm it up or cool it down and put it back into the ground? And also it's very important from the point of view of understanding what that conductivity is, because if you can imagine, if you've got wet rock, it's going to be more conductive than dry rock. So it's got a bearing in both sides of things. The final thing to talk about, and this is particularly relevant to the spacing between boreholes, is heating and cooling systems. So if we are heating only, then it almost always helps us to push those boreholes as far apart as we can. Okay, I'm going to show you what this is called a GMAP of a bore field with 6 boreholes in it. I'm going to show you a real example in just a minute. If we've got heating and cooling loads going on, then it can very often help us by pulling those boreholes together. So if you've got a heating and cooling system, 6 meters is not uncommon as far as spacing is concerned. But if you tried to do that with a heating only system, you would need an awful lot more borehole, because the boreholes are in such close proximity to each other. They're just sucking heat out of the ground. You're dealing with less ground. So you need less borehole, the more you can spread it out in a heating only system. Okay, any questions on that one?
No questions at the moment, Chris. No.
Okay, cool. Natural resources that can help and hinder. We also do have to consider not just the geology and the hydrogeology, but other factors. So are the ponds on lakes there? If we've got any still surface water available to us, it will almost always be the most cost-effective way of installing ground source in a system. Rivers and canals can also help, but they're a little bit more difficult to deal with because the water in rivers is moving, and canals are a relatively limited resource. And I think the Canal and River Authority do tend to shoot themselves in the foot as far as utilising them is concerned. I'm not saying it can't be done, but it needs to be considered. As is shown in the drawing there, and we'll cover in the part 5 of this series, we can interface with mines as well. And I'll talk in that series about the limitations and the challenges associated with dealing with mine water. Aquifers, as I've mentioned before, can help us from a closed loop point of view, from a shear conductivity point of view, and can also put open loop on the table for bigger projects. I tend to think of open loop really coming into its own on project above 250 kilowatts. But there is a member of the Ground Source Heat Pump Association who only do open loops for houses. They've got a specialism in that. They've got a limited geographical area they work in, and they do quite well. So it's a useful technology to have. And then the other thing to think about is other surface features. So something like trees. You know, generally speaking, you can't drill a borehole or trench under the canopy of a tree because you will be damaging the roots of that tree. Other features like slopes, we've talked many times in the past where Geodrill or whoever's drilling a borehole go out to site and say there's no way I can drill there because it's just too much of a slope on the site. So we've got to consider all of the resources, buildings, everything else on the site. What's easy to drill boreholes in, what's difficult to drill boreholes in terms of the geology as well.
Okay, Richard Jones is in with a nice question. Does depth and flow rate have any bearing on the design of ponds and lakes when it comes to working out what's needed?
Yeah, absolutely. So the main energy transfer in a body of surface water is the surface. So solar gains will warm that lake or pond up and evaporative losses will cool it down. On depth, rule of thumb, you need 2 to 3 meters minimum depth. But if you do have something shallower than that, don't rule it out. It just needs a little bit of a different approach as far as design and what we put in the lake is concerned. Okay, does that help?
Yeah, well done, Chris. Steve's in with another question. What is the maximum gradient for drilling, and can this be overcome by potentially landscaping beforehand?
It would vary by driller as far as the maximum gradient's concerned. I've seen drilling going on in slopes up to 45 degrees, but most drillers won't tackle that. So it varies by the driller, by the equipment they've got, and whether they're experienced at drilling at gradients. But generally speaking, if you can't walk up it comfortably, then it's going to be difficult to drill in. That's probably the best rule of thumb for it. What was the other part of that question, Dunks?
That was in relating to, can it be overcome with landscaping? So.
Right, absolutely, yeah. I mean, one of the things about any landscaping that's going on a site is that it's worth considering that landscaping in terms of what are we going to do from a point of view of putting pipe in the ground. So sites that are being leveled, for example, you know, one area is higher than the other, you can put pipe on the ground and then just bury it, you know. So that can be a very economic way of installing horizontal systems. So any landscaping that's going on is absolutely worth thinking about.
Nice question in from Ben relating to geology. What depth are the maps typically showing for bedrock and groundwater? Are there any BGS link showing maps that allow you to change depth, showing subsequent change in the geology type? And he has gone on, I particularly like this bit. Borehole records can be helpful to look at for overall change in geology for a specific location, if you can read the handwriting. And there's the teacher in me coming out.
Yeah, I've had to resort to get my daughter to read some of them because particularly the copper plate writing just messes with my dyslexia, I'm afraid. But yeah, borehole logs are an incredible resource. You know, we've got more borehole logs per square metre in the UK than anywhere else in the world because geology was invented here, the Industrial Revolution and everything else. I did talk briefly about the complexity of UK geology last time, but it is incredibly complex. And that's one of the reasons why the Industrial Revolution happened, is because we've got the complex geology. It's got minerals, it's got coal and everything else available. No, unfortunately there isn't. The BGS have been working for it. The BGS's borehole drilling tool, they've been talking about for at least 20 years now. And the idea is that you'll be able to go to a map, put an X on it, and it'll theoretically drill a borehole for you. They've been talking about it for 20 years. It's kind of like nuclear fusion. When I was at uni in the 90s, it was 25 years away, and it's still 25 years away. I genuinely think it's too complex to do with current technology and the resources they've got available to them. But so unfortunately not. There are some 3D models in some geographically limited parts of the UK, like Glasgow. There's a 3D model built up for that, but they are extremely limited. Good question.
And the handwriting can be an absolute mess.
Oh, it's a nightmare. Yeah.
Joe's in with a question. You mentioned taking heat from water, the fact that it can often be the best method of heat extraction using open loop systems.
Yeah.
Does the ongoing maintenance costs represent greater risk / potential ongoing problems than sticking to closed loop?
My rule of thumb is if you can't do closed loop physically in terms of you've got enough space, technically or economically, then you absolutely should do closed loop. So, you know, you do open loop as a, if you can't do closed loop is the best way I would put it. I'm going to talk about the risks associated with open loop in the fourth of these series. So hopefully that suffices for now, but I will talk in a bit of detail about it. No matter what you do with open loop, you've got risks associated with the drilling of it, and you've got risks associated with the ongoing operation of it. There's nothing you can do about that.
So and risks associated with actually achieving the yield in the first place.
Yeah, that's part of the drilling risks. Absolutely. You know, you can drill the best constructed water well ever made and get nothing out of it. You know, that is a risk associated with it. So I'll talk about that in a bit of detail in session 4. All right.
Lovely. No more questions.
All right, great. So I'm going to do a very quick demo of ground loop design in the package we use, which is called GLD. We also use another package called Earth Energy Designer, EED. I'm not going to demo that today. I don't particularly, we took on EED just over a year ago to back up GLD. We probably won't be renewing our license when it expires because it's got a very significant weakness in it, which I'll talk about when I show you in GLD. Okay, so this is GLD. Now, unfortunately, I can't make it any bigger as far as zoom, so hopefully you can see this. So the first thing is, remember back with the drawing of the 2 heat pumps, heating and cooling, the design process is what's going on in the building, what's the heat of extraction, heat of rejection in the building, what's the properties of the heat pump, and how much pipe do I need to put in the ground as a result. That's the design process in a nutshell. So in GLD, this is where we put the loads in. Most of the time we're using monthly loads. So this would be a load summary that Mark Fontaine's team would have provided for us. And we put that load summary right into GLD. And that's a peak load on a monthly kilowatt hours that's delivered. So it's a heating only system, 24 kilowatts peak, and it's delivering 78,127 kilowatt hours over the year. When we hit update on this, it gives us a summary here, which is like a design day, worst case day. And it also gives us this full load hours, which is a useful quantity. If you're new to the industry, divide your annual kilowatt hours by the peak, and it will give you a number, which is the equivalent full load hours, we call it. Get a feeling for that. It's a really useful quantity. Emily has just recently joined us, and she processed a set of loads for us last week, and the totals were awry. And I saw it straight away. We're only like 115 full load hours in a year. But you know, so it was a good experience for Emily to see something that was unusual. You should be seeing full load hours somewhere between 1,200 and maybe 3,400. So this is right up at the top end of that full load hours you would expect to see. So we've told it about the building. We then select a heat pump, and in the background of GLD, there is a 3-dimensional map of heat pump performance. So if you imagine the horizontal axis is load temperature, the other horizontal axis is the source temperature. The vertical axis would be, there's 2 of them actually. One of those axes is how much power the thing's consuming, and the other one is what the thermal output of it is. So as we go up in temperature in a heating system, we lose both output and we consume more electricity. And we can cover how efficiency in heat pumps works. I think I did a bit of it last time, so you can see that in there. So it's got a 3-dimensional map of heat pump performance built in, and that's the big weakness of EED. It doesn't have this 3-dimensional heat pump map built in there. We select a heat pump, so we Kensa Evo 13, which was selected. We give it the details of the load temperature. So this is entering water temperatures that will be in the specification for the job. And then we go over here. So we've told it about the building, we've told it about the heat pump, and this is all about how much pipe do we need to put in the ground. So it's not a particularly friendly piece of software, but it's very utilitarian kind of. You tell it about the fluid, so ethylene glycol. You tell it about the soil conditions, and this is where the geology all gets inputted, temperature, conductivity and diffusivity, as I mentioned earlier. We then give it the characteristics of the borehole. So is it a single U-tube, is it a double U-tube, is it coaxial in there? Is there a pipe being pushed to the outside of the borehole? What diameter the pipe is? What the flow in that pipe is? And I'll talk about hydraulics of systems next time. So is it a laminar flow, so a smooth flow, or is it a turbulent flow? And we'll talk about that next time. Diameter of boreholes, grout conductivities, and so on. We then give it a pattern. So in this instance, it's a simple 3x2 grid on a 12-meter spacing. And we then hit calculate. And what we're looking for is 0 degrees coming back at year 20. The reason that's gone red is it's less than 0.5 of a degree, but it is under 0. But it's just a rounding thing in there. So if I add an extra, say, 10 meters to that bore field and hit calculate again, then that number will go up. So our minimum water temperature is going to go up. And you can graph that over the 20 years of the simulation to see what your ground loop temperatures, how they're going to be evolving over that time. So that's your minimum temperatures and your maximum temperatures. These graphs become much more interesting when you've got heating and cooling systems going on. And then the final thing we can do with this, and it's out of interest really, is we can plot these what called GMAP functions. And these are actually the equations, a pictogram, if you like, of the equations that GLD is using to predict what each individual borehole is contributing. And you can spin them round. And what you see here is the boreholes in the middle, their graphs are a bit higher because of the proximity of other boreholes on either side of them. They are contributing less to the system, or put it another way, are under a bit more pressure. So you can look at that. Sometimes you can see if you've got a big bore field with boreholes in the middle, you could get rid of a borehole in the middle and actually make very little difference to the overall depth. So that it just allows you to assess how effective the system is that you're designing. That's a relatively very high level view of what's going on. Other things we can do is we can plot accurate borehole locations in this, either by using this grid builder thing. So I can make an L shape or make an L shape like that and just add that in. So I can do those kind of things, or we actually use software outside it to accurately plot boreholes and import them in as comma-separated value files into the software. Just very quickly show you horizontal systems. Most of it's pretty much the same, but when you go into configuration, you've got a huge number of options here. So it's always worth trying to explore the options. We're working with Worcester Renewables, one of Kensa Heat Pump's customers, over the last few days. They've got horrible ground. It's like big chunks of limestone and clay in this ground. And we tried various different options to get the best trenching installation solution for them. So we've got slinkies laid flat, we've got slinkies on their side. We've got my favourite, the 6-pipe trench, which is 3 pipes flowing out along the bottom and 3 pipes coming back, and so on and so forth. So huge amount of options you've got when it comes to horizontal systems. Any questions in on that, Duncan? Okay, cool. So that was a demo. It wasn't a training course, obviously, in GLD, but it just gives you an idea about what we are doing to get the ground loop designs. I'll dip back into GLD next time to look at the hydraulics module that is now available in GLD. We use that now as well.
Cool. Alistair's asked, is there an inbuilt or built-in safety factor for borehole depth? I'm guessing that's in relation to the designs we issue, Kensa.
There isn't, no. There isn't. What you tend to find is if you give it monthly loads, it will be less aggressive is probably the right word. If you give it hourly data, you'll tend to find that you get smaller bore fields out of the thing. So it'll add a little bit less in, but no, there isn't actually an inbuilt safety factor in it. You do tend to be a little bit conservative in terms of the loads required for the building and the conductivity, your ground conditions, if you're not doing conductivity testing, which I'll talk about next time. But no, there isn't a safety factor built in. They used to have a safety factor built in, but they actually took it out.
That's it.
Okay, cool. So just building on that then.
Sorry, Chris.
Sorry.
Does the software look at climate change temperature increase over the next however many years?
It doesn't, but we can do that. So yes, we can do it, but it isn't built into the software. Very good question. Okay.
That's
so
it for now. Yep.
All right. So some questions to our client, which will partly be a sales tool, but also partly help us design better borefields for you. So basics, obviously, we can't really do an awful lot without location, what space we've got available to us, the loads. Now we can calculate loads just based on square area, same as yourselves. But we need to know some kind of loads for the building. In all the business that we do for non-installers, it's almost always consultant engineers will be providing those loads, and we'll be having a conversation with them regularly about it. We're also interested in what distribution temperatures are going to be. So if we are heating at a higher temperature, the heat pump will be less efficient, therefore it's going to draw more electricity. And back to my earlier slide, that electricity is going to contribute positively to your heating, and therefore you need less loop in the ground. So a more efficient heat pump is going to need more loop in the ground, and that's a common misconception that many people have. And then heat pump selection is always useful to know. We can make an assumption that it's a good efficient heat pump like an Evo, or it's a basic heating and cooling system. We can pick a heat pump that will be in the ballpark, but if we know what heat pump we're dealing with, it's always going to be that bit more accurate. And then other stuff, useful stuff to understand, both from the point of view of design and from the point of view of selling the job. Site plan is always very useful. What's the client's appetite for risk? So some clients will just rule out open loop entirely. And again, I'm going to talk about the risks associated with open loop in a future session. What's the drivers? And this is really fascinating in the policy world at the moment. So is a decarbonisation agenda on the main driver for this? What is your counterfactual? Is the fuel you're displacing gas? Is it electricity? Have we got heating and cooling associated with it? There may be planning requirements, which is driving a project away from gas and away from direct electric towards heat pumps in general. So it's worthwhile considering what those client drivers are. Have we got any broader opportunities? So is an energy service company a possibility? Is a district network a possibility? Get to know the M&E engineers is always very useful. They can be, frankly, difficult to deal with at times, but they're part of the customer team. And what I tend to find is the bigger engineers have better quality people generally, and so they tend to be quite easy to deal with once they sort of understand your capabilities. Have we got any existing building issues? So retrofit scenarios, what are we looking at distribution wise in those buildings? It's very unusual. You're going to have to rip the whole lot out and start again, but it can happen. And then any plant space requirements, rooftop space restrictions and so on, they are also useful to understand. So that's a bit of a brain dump on what's the useful information to build and base good quality ground loop design on. I'm just going to touch now on heating and cooling loads. So one of the big benefits of ground source systems is that they can actually store energy in the ground, and that heat can be stored between summer and winter. This is our profile from a real building we're designing in London, which hopefully will come to be constructed fairly soon. And you can see that the ground loop temperatures here are up at about 35 degrees in the summer, and they're down at about -4 at the lowest in the winter. This is a single year of data. So what we're actually doing is we're recharging that battery. And if the ground conditions are right, then that can actually amount to genuinely interseasonal storage of energy. That gives us greater efficiencies, and it actually might mean that we need less borehole in there because we're putting something back in, recharging that battery. So anytime there's cooling available to us, then absolutely grab it by both hands. One thing that breaks my heart is when you see a spec for a school come from a consultant engineer and they're saying it's going to be 100 kilowatt ground source doing the heating, and you ask them, yeah, what's your cooling for the server room and for the the ICT suite and all that? They say, no, we're going to do that with a split. That's heat that can go back into the ground. You know, that is going to improve your heating efficiency. It might reduce your ground loop requirement, and by the way, your cooling is going to be done at massive efficiencies. One building that I designed about 15 years ago in London, one new change just by St Paul's Cathedral. It's 3 layers of shops and restaurants, then 3 layers of offices. And there's a very nice rooftop bar, which is a fabulous place to have a drink, particularly in the evening in London. And last time I got some data on it, we were achieving an annual seasonal COP, so not a spot COP, but annual across the whole year of 4.8 in heating. We were at 6.8 in cooling, so really massive efficiencies. You know, there's no other technology can get close to that. Any questions on that?
No, we're clear of questions at the moment.
Okay.
If you do have any questions, please feel free to type them in the chat.
Okay. As I mentioned earlier on, monthly data is considered the absolute minimum requirement for systems, and most of the designs we do for Kensa will be based on monthly data. However, if we can get hourly data, it just gives us that bit more accuracy in what we can achieve, and that's particularly true when we're looking at hybrid systems. This is an example of a system which is conventional equipment, actually air source, ground source hybrid, and we can make really accurate calculations about how often that auxiliary plant is going to be used, what the efficiency of the overall system is going to be, but we can only really achieve that with hourly data. It gives us really fabulous control over the design. The other thing that's really beneficial, and those who've been at Kensa for any time at all will understand, we're always asking about, can we have plotted locations for boreholes? So if we've got 2 boreholes that are a bit closer together and 2 boreholes that are a bit further apart than just a regular grid, then that's going to impact performance of that system. And almost always when you go to plotted locations, as opposed to just a regular grid, you're saving borehole numbers or borehole depths, overall drilling depths as well. And then finally, thermal response data. So that's going to be the opening topic for next week, is to talk about how we actually capture the physical properties of the ground. I'm going to show you how that works, how that process works. But what that does is, rather than having estimates in those boxes in GLD for undisturbed ground temperature, conductivity and diffusivity, we've got measured values. And almost always we are measuring higher values than you would prudently assess from the desktop. Obviously, we don't want to be over-assessing conductivity if it's just a purely desktop study, because that would cause us performance problems. So we're always a little bit conservative on that until we get the thermal response data, and then we can be very, very accurate. Okay,